Hello and welcome to the BinarX Student Payload Development Program Week 5, Introduction to Orbits. An orbit is a regular repeating path that one object takes around another object, or center of gravity. And it's the path that our CubeSats take, which in the case of Binar 1, 2, 3, and 4 is around the Earth. So today we're going to look a little bit at orbital mechanics. So we're going to look at how orbits work. We're also going to look at the orbital elements that describe the shape and orientation and position of our orbits, and also our spacecraft along the orbit. We'll also talk a little bit about LEO, MEO, and GEO, which are terms you hear a lot in relation to satellite orbits. We aren't going to get right down into the maths, although there is some lovely math, but the purpose of this week is just to familiarize yourselves with the basics of how orbits work and some of the terms used to describe orbits, which you'll need for the activity next week, where we model the orbit of a satellite. So this week, we want to understand and apply basic terms applicable to orbits, explore the basics of orbital mechanics, and explore a few different kinds of satellite orbit. But first, Binar Space Program updates. Our team has arrived safely in Japan with Binar 2, 3, and 4, and have rendezvoused with Kyo and Kubo from our launch broker Space BD, who then went on to meet with JAXA to hand over the satellites. So watch this space for more updates. Today we're going to talk about the basics of orbital mechanics or celestial mechanics or orbital motion. We're going to look at how orbits work, how you get into orbit, and the basic shape of an orbit. So if we think about parabolic projectile motion, if that's something that you studied already, perhaps in physics class, you think about how something flies when you fire it out of a cannon or a tennis ball launcher, what path it takes and sort of curves down. It's that sort of not a straight line, it kind of curves down like in a parabola. So if we had a cannon, a really big cannon sitting on the Earth's surface, and we fired it, we would get a parabolic trajectory, or a trajectory that's well approximated by a parabola, and that's what we were just discussing. So I want you to think about what happens if we put more gunpowder in the cannon and the projectile goes further and further. So at some point you can see the parabolic approximation starts to break down, so it becomes sort of less and less of a parabola, and that's because the direction of gravity starts to change with respect to the motion of the projectile during the flight. And so as the direction of gravity changes relative to the projectile's frame of reference through the flight, the projectile motion actually starts to curve around further and further around the Earth. So you could replicate this. It's hard to see, but if you took a tennis ball and let it roll off a table versus, giving it a good push off the table, it wouldn't take any more time to hit the ground, which is quite fascinating and a little bit hard to get your head around, but it's that's something you guys can try. So at some point, if we put more in, it would travel all the way around the Earth and come back and smash into the back of our cannon. And if we were able to move our cannon out of the way, we would actually be in orbit. So the only problem is we're going to pass right back through the position of the location of the cannon. So yeah, you'd have to move it. But if you got a really tall tower, maybe 400 kilometers, to get you to where the air drag was low enough, and you had a big enough cannon at, somehow high enough at that altitude, you could put something into orbit with a cannon. But we do have better ways of putting things into orbit. It's not actually how we do it, but it's an interesting thought experiment. So this circular orbit, it would actually repeat. But if you were to put even more energy into the cannon, you would get a different shaped orbit. Can you think about what the new orbit might look like? So we're actually going to end up with an ellipse instead of a circle. And as we put more and more energy in, the ellipse gets bigger and bigger and goes more out one way. So as we put more energy in, the Earth's gravity will still bend that trajectory around, and that's why it ends up coming over out the side. So if we were to put even more energy into the cannon, at some point the projectile would have enough energy that it would travel far away enough from the Earth that it would leave what's called the Earth's sphere of influence and not come back. At which point it's called an unbound orbit, which we won't get into today. We're just going to discuss bound orbits. So for the bound orbits that repeat, they'll actually be captured by the Earth. So another important thing to think about and discuss is the shape of orbits. So I said that we can have a circular orbit, and I said if then we put more energy in, we'll have an elliptical orbit. But it's important to remember that a circle is just a special type of ellipse. So actually, all orbits that are bound and repeat, all bound orbits are ellipses. And remember that a circle is just a special case of an ellipse, just like a square is just a special case of a rectangle. And it's also important to remember that because it's special, it's an ellipse where the eccentricity is equal to 0. It's never actually going to happen in real life. So all ellipses are going to have some amount of eccentricity because it's a circle only when the eccentricity equals 0. But these circular orbits are still a useful approximation for the sorts of things we want to do when we're planning our space missions, so that's why we use the approximation. But it's important for you to remember that an orbit that is truly circular is unrealistic, but we can use the approximation, that's fine. So now we know that all orbits are basically formed ellipses when they're bound and repeating. And this is Kepler's first law. So back in the 1600s, Johannes Kepler was studying the motion of the planets, and he came up with Kepler's laws and he published them. And we have Kepler's laws which govern planetary motion, which we still refer back to today. And these have all arrived now, and they're on their way out. But if you have a look at page 36 and 37 on how space works, whoop, it's not going to let me focus. There we go. Well, the book that you're all receiving, there is a little summary of Kepler's laws, which is handy as a reference. So if you're interested in the history of this, there's a video on the lesson plan for this week in the video resources that goes in depth into them a little bit more and a bit of interesting information about what was going on at the time and sort of the historical context of the discovery. But we'll just get back onto what they mean for now. So Kepler's first law states that the orbit of each planet around the sun traces out an ellipse with the sun located at one of the focus points, one of the foci. So here on this ellipse, you can see two foci, F1 and F2. And F1, the one on the right, is our sun and on this diagram. So the planet is the satellite in this case. It will trace out this path over the ellipse as it goes around the sun. Now, it might be an ellipse that's quite close to a circle, but it might be an ellipse that's not very close to a circle. And we call this stretch or stretchiness, this sort of elongation of the ellipse, we call this the eccentricity. And a circle has an eccentricity of 0, and an ellipse like this has an eccentricity of somewhere between 0 and 1. And so that is Kepler's first law. And the interesting thing about a circular orbit is that the magnitude of the velocity vector doesn't change as the object orbits around the body, so it's a constant speed. Now, the velocity is not always constant because it's always changing because we're always accelerating towards that body. So we're curving around that body. So the velocity vector is not identical around the whole orbit, but the magnitude of the velocity vector or our speed is constant. So that's in a circle. Well, what about orbits that aren't circles, that are elliptical? And this is Kepler's second law. So Kepler's second law states that if you were to draw an imaginary line between the body and the object that's orbiting, so the sun and say the Earth, that imaginary line would trace out an equal amount of area in space, so in this case A1, over an equal interval across the orbit. So here we've got this imaginary line between our spacecraft and the body, and then the interval is T1. So this is T1 plus our interval time, Ti. So we're going to trace out this area here, A1, in space in the orbit. Now what Kepler's second law says is that amount of area that we sweep out over time, so in that red shaded triangle, is actually constant throughout the orbit, which is quite neat. So that actually tells us a few things about the speed when we orbit around. So if we're further out from our body here, and we're sweeping in an equal amount of area, well, these lines are longer in the second one that was drawn. So this distance must be shorter. So we must be going slower when we're further away from the body we're orbiting. And we must be going faster when we get closer back to the body we're orbiting. And this diagram Here, all three of these areas are equal, so the red shaded areas, and that time interval for each one of these sections is identical as well. So that's pretty neat. So the thing to remember is when you're close to the body orbiting, you're traveling fast, and when you're a long way away from the body orbiting, that's when you're traveling the slowest in your orbit. So there we go. Slowest, faster, fastest. And Kepler's third law is about the time it takes to do a full orbit, which we call the period, but we're not going to cover that today. But it's important to know the term period for an orbit is one. And now it's probably a good time to talk about orbit terminology, or what we call all these different places on the orbit. So here you can see on my ellipse, I've drawn the two foci on the ellipse of F1 and F2. We call that line there that connects these two special points on the ellipse the line of apsides. And this line will become important when we start to talk about orbits in three-dimensional space later on. And so we have our body that we're orbiting, F1, and then over on the other side we have this other focus here, and we call it the empty focus. So we normally just call F1 the focus, but they're both foci. So we normally refer to the body we're orbiting. And if we're talking about this point on the right, because this point F1 is the center of mass of the body that we're orbiting, and this point over on the left, F2, it exists in the geometry of the ellipse, but it doesn't really exist out in space. There's nothing there. It's just part of the geometry of the orbit. And so we have special names for the point where we're closest to the body we're orbiting and when we're the furthest away. And you think, oh, it's just geometry, but when we actually, they're quite useful when we talk about mission planning, because you really do need to know how far away you're going to go and how close you're going to be when you're at your closest. So if you're trying to communicate with your satellite in orbit, how much power you're going to need for your transmitter or your receiver to communicate or receive communications. So that's why these are important to our mission. So the points on our orbit when we're closest and furthest are called the periapsis. So that's the closest point to the orbiting body in the orbit, and the furthest point, which is the apoapsis. And these names actually change. The names of the points will change, of the periapsis and the apoapsis will change if we're referring to a specific or different bodies in the solar system. So if we're talking about the closest point in an Earth orbit, we call this periapsis, we call it the perigee. And if we're talking about the furthest point away in an Earth orbit, we call it the apogee. When we're not talking about an Earth orbit, you might accidentally say perigee and apogee, but you should, still know what they mean. And you should know that the generic terminology is periapsis and apoapsis, and that will change. The specific Earth terminology is perigee and apogee. And if we're talking about orbiting around the sun, the specific terminology is the perihelion and the apohelion. And if we're orbiting around the moon, we have the periluna and the apoluna. And if we're orbiting around Jupiter, we have the perijove and the apojove. So that's kind of cool. And it's helpful because you know which planet you're orbiting around. But just remember periapsis and apoapsis, and also perigee and apogee. They're sort of the most important ones that people normally talk about. So here are some of the geometry of ellipses, which are useful for us when we're trying to calculate orbits. So you've got this on your worksheet. You can start filling out those blanks. The really important thing on this diagram here are the semi-major axis, A, which is basically how big our ellipse is. So as you can see here, it's half the distance between the periapsis and the apoapsis. And another way about thinking about it is that it's half the radius at the closest point plus the half the radius at the furthest point. So you can just take the closest radius and the furthest radius, add them together, and divide the total by 2. One thing to remember, or to not get caught out on if you're calculating this, if you're given the closest point and the furthest points, the perigee and the apogee in the case of the Earth orbit, as an altitude from the Earth's surface instead of a radius from the center of mass, then you'll need to add in the radius of the body that you're orbiting, because the altitude is relative to the surface of the planet or the body. But for calculating semi-major axis, we really need to know the radius from the center of mass. So if you're given the altitude, you'll need to remember that to add back in the radius of the body, so radius of the Earth, when you're doing the math to calculate the semi-major axis. The other really important thing on this diagram here is our true anomaly, is theta, and it's the angle between our periapsis and the current position of the spacecraft. We call that the true anomaly. Now, next week when we start looking up data on satellites that are on orbit, you might get the mean anomaly. You can calculate the true anomaly using the mean anomaly and some other things, but don't worry about that right now. Just know that the true anomaly is the position of your spacecraft in the orbit. And eccentricity as well is the other important one to get off this diagram, because as we've discussed before, that's basically how stretched out our ellipse is. So if the eccentricity was 0, it would be a circle. And if the eccentricity is something like this, it's probably about 0.7. So now that we know a little bit about Kepler's laws, what are the implications of this? Well, now we know the shape of orbits for permanently associated objects. So there's those objects that orbits go around and round and round and round. So for example, Binar going around the Earth. So it's not permanent, but in the case of what we're discussing, we'll call that permanent. We now know what shape they are. They're ellipses, and sometimes they're an ellipse that looks like a circle, where the eccentricity is very close to 0. So that's as much as we'll cover now on how orbits work. There is more to it, like everything we talk about. So if you want to know more about any of this, please get in touch with us on the BinarX email, and we're always happy to answer your questions. Or come up to me and ask, and if I can't answer it, I'll go back and find out from my fabulous team back at Curtin. So we aren't going to model orbits today mathematically, but you can ask us more about it if you really want to get stuck into the physics of it. But when we are going to describe orbits and talk about them when we do our mission planning, it's really useful to have a standardized way of talking about the orbits and describing the orbits. And with these 6 orbital elements is what we'll use. So we've already touched on some of them. The semi-major axis, how big is the orbit? Eccentricity, how circular is the orbit or elliptical is the orbit? So that gives us the shape of the 2D ellipse. And then we're going to talk about new elements, which will start to position our 2D orbits in 3D space. So the inclination is how much the orbital plane is tilted up from the equatorial plane. The right ascension of the ascending node, where the orbit goes up north past the equator. So that's another one. The argument of periapsis and perigee. So on the plane we've just defined, it talks about where the periapsis is. And the true anomaly, which is the position of the spacecraft in the ellipse. So all of these position our orbit and our spacecraft in 3D space. So we'll look at this a little bit more in depth on the next slide. This is probably one of the better 2D diagrams that we've seen that tries to explain the 6 classical orbital elements. And this diagram in particular is from Space Mission Engineering, the new SMAD, and that's in your resources list on your lesson plan for this week. So I'm going to run you through what's going on in some of what's going on in this diagram to help you understand it better. But if you have a look at the interactive 3D diagram that Dr. Robert Howie has prepared that's on your resources sheet under web resources, that's a fun way to do it quickly and start playing around with the values and seeing how they affect each other and getting your head around it. I found it quite helpful. But on this diagram, the first orbital element we'll look at is the semi-major axis, which we've talked about before, the size of your orbit. So you can see in the bottom left corner, 2A, So A being the semi-major axis, and 2A is twice the semi-major axis, and that is the length of the line of apsides. So that's the line that runs from the perigee down to the apogee of your orbit. So that's the first orbital element out of the way, the semi-major axis. So the next one we want to talk about is the eccentricity, and it's not labeled in the diagram because it's not something you can point to. But you can see that this orbit is elliptical, so it's not circular because it's kind of stretched out. So that's the second orbital element, the eccentricity, how elliptical your orbit is, or how much not a circle it is. The next orbital element we're going to talk about is the inclination, and that's the first element that will position our two-dimensional orbit in three-dimensional space. So that's labeled sort of in the middle, just below the Earth's equator, as a lowercase I. So it's measured against the equatorial plane in any frame of reference, and in this case we're using the Earth's equator. So that's the inclination, lowercase I, and how tilted up the orbital plane is. So, if it were 0, it would be in line with the equator, 45 degrees, up like this. So that's a pretty straightforward one, I think, for me anyway, compared to the one we're going to go into next. So the next one that's going to help us position our orbital plane in three-dimensional space is the right ascension of the ascending node. So it's a mouthful. You'll see it's shortened to RAN, R-A-A-N. And we'll talk about that next week. It's measured relative to the vernal equinox direction. So on this diagram, it's on the left-hand side, and it's labeled with the Aries symbol that looks like a bit of a ram's head. So the vernal equinox direction is when the center of the the sun is aligned with the Earth's equator. So the center of the sun and the Earth's equator aren't always aligned because of the tilt of the Earth, but twice a year it does line up. And in March we get the vernal equinox. So the vernal equinox is when the alignment of basically the center of the sun is moving from below the Earth's equator, from the south, ascending into the northern hemisphere across the equator. So so even though we have equinoxes twice a year, and you probably hear about them, we're only going to concern ourselves with the vernal equinox. So at that time, when the center of the sun and the center of the Earth are lined up, the equator, if we drew a line through the center of the Earth and the center of the sun at that point and left it there, that's our vernal equinox direction. And that's what we're going to use as the reference point when we use to get to the angle of the right ascension of the ascending node. So the right ascension of the ascending node on this diagram is shown as capital omega, and that's the angle between the vernal equinox direction, so that line we drew and left there, and the ascending node of our orbit when our spacecraft goes up from through the equator in the ascending direction from the southern hemisphere to the northern hemisphere. So that point's called the ascending node, and it's measured relative to the vernal equinox direction. So the symbol we use for the right ascension of the ascending node is capital omega, and the line drawn from the ascending node of the spacecraft over to the descending node, which is where the spacecraft does the opposite, goes from north to south, we call that the line of nodes. So the right ascension of the ascending node, capital omega, is what positions that line of nodes for us. So next orbital element we want to talk about is the argument of perigee, or the argument of periapsis. I didn't explain that one very well a few slides ago, but it's easier to talk about now that we can see it on a diagram. So this is lowercase omega, which looks like a little w, as the argument of perigee, or the argument of periapsis, if you're talking about it more generally. Not just about Earth orbits. So periapsis if it's anywhere, perigee if it's an Earth orbit, something orbiting around the Earth. So that's the angle, lowercase omega. So here it's labeled between the ascending node and the perigee of the spacecraft. So it's labeled, so the angle between that point there on the line of nodes. That vector there and that vector here from the center of mass. So basically we go from the ascending node through the center of the Earth up to the spacecraft when it's at its perigee. We use the simple lowercase omega for that one, and it's called the argument of perigee and the argument of periapsis. So if you varied the argument of periapsis, you basically rotate the ellipse on the plane that has already been defined by the inclination and the right ascension of the ascending node. So you can think of it as not defining the plane in 3 dimensions because it's rotation of the 2D ellipse, or you can think about the rotation of that reference plane that we're creating in 3 dimensions. It doesn't matter. You can think of it either way, but basically it rotates the orbit around the center of mass relative to the ascending node direction that we just established. So the last element we want to talk about is one you're already familiar with, and that's the argument of, the true anomaly. And that's the angle between your perigee, or your periapsis, and the current position of the spacecraft. So that one is labeled with the Greek letter nu, which looks like a lowercase v, which is the symbol we use for the true anomaly. So that one is a little bit more straightforward than some of the others. It's basically how far around the orbit from the perigee you are. So I think the really trickiest one here is probably the right ascension of the ascending node. That was the hardest to my head around, because it's relative to a reference direction that's difficult to conceptualize. So it's probably easier for you to go look at the other resource video, the NSSI video on your resource sheets, on your lesson plans, and the interactive diagram that Dr. Robert Howie has prepared for you. Again, the link is on your lesson plan page from today. And get a feel for that rather than me just keep talking to you about orbital elements, because you'll get a much more intuitive understanding from exploring that yourself and discovering with that diagram. And we'll just quickly touch on a few different orbit types for satellites and acronyms. So we've got LEO, low Earth orbit. CubeSats are often found here. It's an altitude of roughly 160 to 1,500 kilometers above the Earth's surface. They have a short orbital period between 90 and 120 minutes, meaning they can travel around the planet up to 16 times a day. Medium Earth orbit, or MEO satellites, they're located between low Earth and geostationary orbits, typically at an altitude of about 5,000 to 20,000 kilometers. Positioning and navigation services like GPS extensively use MEO satellites. Ooh, there we go. Sorry. Ooh, shadows. And they usually have a longer orbital period of somewhere between 2 and 12 hours. So it's data transmission, things like that. And GEO, or geostationary orbits, they are positioned about 35,786 kilometers above the Earth's surface, precisely over the equator. So they can effectively, their orbital period is identical to the Earth's rotation, 24 hours, but not quite 24 hours. It's 23 hours, 56 minutes, and 4 seconds. So this allows a terrestrial antenna that doesn't have to move very much to always point towards the same device in space. So this type of satellite is perfect for always-on communication services like TVs and phones. Also, this type can be used in meteorology to keep an eye on the weather for a specific spot. So yes, they are. The downside is that real-time communication is tricky because the signal takes it's a longer delay because it's so far away from the Earth. So here is a little animation. We got LEO, we got MEO, and GEO. Diagram not to scale. So that's it for this week. Next week, we will talk about ground tracking and understanding where a spacecraft will travel above the Earth, ground track. If you go into the web resources for this week in the learning lesson plan, there's a link to a software called GMAT, General Mission Analysis Tool, and it's actually NASA open source software that does get used in mission planning. You can download it and open it up, and I'll take you through putting in some parameters, and we can actually start to model some orbits, and it's quite fun, quite addictive. And then you'll be able to sort of, if we were to say model the ISS, that will give you a good approximation of potentially where your payload will travel when it's on board of Binar, and that can we can use that to refine your mission concept to see when and how often and where your payload is going to travel and sense above the Earth. So thank you very much, and we'll see you next week.